bond model. So you have seen this kind of figures before, where we draw the dopants and the electrons. So in this case, we have in this case we have p-type substrate. So we have the acceptors, which is Na minus, and then we have the holes, which is the plus sign here. So those are the holes. And then you have the Na minus, which is a fixed charge by the acceptors nuclei. And then let's say this is the MOS structure. So we draw it horizontally. Previous we draw it vertically, but now let's draw it horizontally. This is metal oxide, and this is the silicon semiconductor. So then we apply the gate voltage to the metal, and then let's ground the silicon substrate like this. So let's look at how the holes move in this process. So let's say this is gate voltage 0, and when you apply gate voltage, for example, positive 0.1 volts, so you will apply some positive voltage to the metal terminal. Then what will happen here, you see this animation, you are going to repel the holes away from the surface. This is the surface between the oxide and silicon. And then let's keep increasing the gate voltage. This is a depletion, as we discussed. Let's further increase the voltage to 0.2 volts. So you have more positive charge to the metal, and then you are going to repel more holes away. So then this depletion width will further increase. And you know this Na minus, this negative charge, are going to balance the positive charge to the metal. So this is net capacitor, right? MOS, this is net capacitor. You know, capacitors, two plates, the charge need to balance. If one plate has positive charge, the other plate will have the same amount of negative charge. That's the property of the capacitor. So let's keep doing this. If you further increase gate voltage to 2.3, and then you are going to repel more. So depletion will further increase. So let's keep doing this. And then this is a tricky point. Okay. Let's say this is 0.5 volt already. Now if you change to 0.6 volts, then this depletion width will not increase anymore. Because when you repel those holes away, and then this Na minus, okay, you are not going to get one more Na minus, because here those Na minus are too far away from this capacitor structure. So this, for example, this column of the negative charge cannot balance the positive charge to the metal when you further increase, because they are too far away, right? And you know the capacitor structure, you need somewhere near this surface. So the only way to balance one more positive charge to the metal is to induce the negative electron to the surface. So now you see here we have the electrons. This is to balance the positive charge on the metal plate. Because here those are not effective, they are too far away. It's too far away. So if you this, and then this is a inversion. So if you keep increasing the gate voltage, you are going to induce more and more electrons here. So you see here more and more electrons. So basically, those number of electrons will balance the increase of the positive charge to the metal plate. Any questions? Okay, so this is this band model, but we really like this band model. Okay, let's look at from the band model point of view how to create inversion. So this is a quick review, and this is a band diagram for the N-type semiconductor. And you know the EF is close to the EC. And then this is the P-type semiconductor, where the EF is close to the EV. And here, this is the equation to calculate the electron density for the N-type and the hole density for the P-type. Okay, so let's look at the MOS structure. How to create inversion? Inversion means what? If you look at this N-type versus P-type. So the only change is that you need to shift the Fermi level. Right? For example, the P substrate. Initially, the Fermi level is here. But after you create the inversion, then the surface becomes N-type. Then in surface, the EF should be moved up to somewhere here. So in other words, if you look at one piece of silicon, initially, then the Fermi level should be down, close to the EV. And then, after you create this inversion, you see this animation, right? So the Fermi level should be close to the EC. So it's not, you are going to shift the EF. Or if you think the EF does not move, then you need to shift the EC, because those are relative distance. Okay, so what does this mean? Let's look at this amount of energy you need to shift. Let's say this is before. That means P-type initially, when the gate voltage is 0. And then this is at the threshold voltage, P-type substrate. And then at the threshold voltage, the surface becomes N-type. So let's define the threshold voltage as where the surface becomes N-type and the surface electron density is the same as the hole density to the substrate. So if you have this kind of assumption, then you see the Fermi level. So here we have this phi b. That is distance between the EF and the intrinsic Fermi level, where is the let's say the half of the band gap. So you can see that here, in order for you to create this inversion, the EC needs to be moved down by 2 phi b. Why is that? Because initially the Fermi level is below the EI by phi b. At the threshold, now the EF is above EI by phi b. So that means the EC moved down by by 2 phi b. So that is a condition to create inversion. And you know how to calculate the phi b. So if you recall your homework 1, then you can first calculate this distance, which I believe will be like kt log like n v over na doping, depending on the p-type doping, where you can get this distance. And then you know the ei to the ev, because ei is intrinsic Fermi level, that is half of the band gap, half Eg. So you know the phi b is half Eg minus this kt. And here you need to have 2 phi b to get this inversion. Any questions here? Okay, so here it says that these two have the 2 phi b. Okay, so let's look at the MOS structure. So here is the MOS. Depending on the material, you have different metal, different oxide, or different semiconductor. Then you have different kinds of band diagram. So for the, let's say, for the oxide here, there are different kinds of oxide in this plot. I will not go into the details, but basically different oxides may have different band gap. And the silicon dioxide here, this one, this is the band gap for the silicon dioxide, and it's very large. So we draw it here. It's around like 9 electron volts. So silicon dioxide. And then the silicon here is what we have before. So it's like 1.1 electron volts for the silicon. And then here we have this EI in the middle, and then the phi b for the p-type substrate. So this is the vacuum level. We need to discuss this vacuum level. This is an energy level where the electron is in the vacuum. Or in other words, if you want to reach that level, you need to kick out the electron from the silicon. So electrons used to be here, right? Like the conduction band edge, EC. And then if you want to kick the electron from the silicon to the outside, let's say to the vacuum, then you need to apply this energy, like 4.05 electron volts. And this energy is called the electron affinity. And then the electron will reach the vacuum level. And then for the metal, it also has a band diagram. But as we discussed before, the metal has no band gap. So in other words, in the metal, there's only one Fermi level. That's it, where all the electrons, most of the electrons stay there. So the metal is just a single Fermi level here. This is metal, for example, aluminum. And then similarly, for the electrons in the metal to jump from this Fermi level to the vacuum level, there is a electron affinity. And sometimes this is called the work function, metal work function. And phi m So let's define another term here, which is this phi s. So this phi s is the distance between the vacuum level down to here to the Fermi level for the semiconductor. As you can see, this phi s is the electron affinity, this one, plus the half of the band gap, which is this term, and plus this phi b. So 3 segments, let's say from this vacuum level here down to the EF. Then you will first have this electron affinity, and then second is the half of the band gap, and third one is this phi b. So this is the phi s. And then you have the phi m. Of course, this phi m and phi s depends on the material. So here in this chart, it shows the different materials band diagram. Those are like semiconductors, and here are the oxide. Okay, so why does this matter? Because we have to assume the phi m equals to phi s. To simplify the discussion here, we'll assume the phi m equals to phi s. That means without voltage, the Fermi level of the metal will be the same as the Fermi level of the silicon. This may not hold in most of the practical scenarios. But for our discussion here, we'll assume this happens. So this is also called the flat band condition. So here we are drawing the band diagram of the MOS. MOS. So we are looking at this capacitor, MOS. And you know the metal, as we discussed, there's only a single Fermi level here. So this is a Fermi level for the metal. And oxide has a very large band gap. Very large band gap. And then the semiconductor here is p-type. This is p-type. So we have the band diagram like this. This is the silicon p-type, and you have seen this before. So here, the Fermi level is lined up between the metal and the semiconductor. So this is the equilibrium state. And as we discussed before, in a single system, the Fermi level, there's only a single Fermi level. So the Fermi level should be flat. Previously in the p-n junction, no matter p-type or n-type, then you have a single Fermi level flat. So in this MOS structure, similarly, you have a single level Fermi level. The metal and the semiconductor will have the same Fermi level. So and this is a flat band without voltage. So the gate voltage equals to 0. Of course, this happens under this condition, phi m equals to phi s. There's no built-in potential here. Now we will see a few scenarios. Let's say gate voltage smaller than 0. So if gate voltage is smaller than 0 for this MOS structure, your substrate is p-type, that means we apply negative voltage to the gate. Then what will happen from the band diagram point of view? Any idea? So we need to apply the conclusions we discussed before. So positive voltage means what to the band? Negative voltage means what? If you recall, positive voltage, let's say, will push down or pull up?
Push down.
Push down, okay. Then in this case, negative voltage here will pull up the Fermi level. So the Fermi level will be pulled up by this. Let's assume this side is grounded. Then you apply the gate voltage to the left. That means to this end it will be flat. That means no change. It's ground. So you only change the metal Fermi function here. So then Fermi level is up. So if this Fermi level is up, so the band will be all pulled up. This band will bend like this. So if band is bent like this, that means here you are going to get more holes. You can understand this either from the, let's say, from the band bending point of view. You know the holes try to move up like bubble. So if you create the triangle region to the surface, then here you are going to have more holes accumulated here. So that means these holes will accumulate to the surface. This is true because you apply negative voltage. That means you have many negative charge to the metal. Then you need more holes to balance this charge. Okay, so then let's look at the positive voltage. This is what we discussed from the bound model already. So positive voltage, that means the Fermi level of the metal will push down. Then everything here will be bent like this, because this is down. So then it will bend down like this. And then that means what? So if this is bent down, then that means less holes. Because those holes are repelled away, as we discussed. Less holes. This becomes a depletion. If you keep increasing the gate voltage, for example, larger than threshold voltage, then this band is so bent here. So here, you know, this triangular region, you have electrons. Because electrons tend to go down in the band. So you create electrons. This is inversion, because you need to balance the positive charge by the positive gate voltage here. This is inversion. So any questions? So this is how you understand this process through the band diagram.